Good morning, everybody. I have this small phone here with the slides because I need to know what's coming next to be fluent. English is not my native language, so sorry for that. The lights here are showing me the future. The future will get rid of the factors safety at all. So there will be a point in time that we will no longer talk about factors safety. This already happened, for instance, in structural analysis. Eurocode 7, which is now mandatory, creates a framework for semi-probabilistic methods for structural integrity that take into account the uncertainties of the various factors that contribute to a given behavior. So for instance, if you have a tower, the wind will have a large uncertainty, and then you will deal with a factor that will take into account that uncertainty. If it's not a tower, this is a flat thing, the wind plays no role and the factor is different. And the factor of safety is kind of diluted into the separate contributions of various sources of uncertainty. It's not easy, it's a journey. We're going there. It's not, those are not the lights of the screen. We are going there. It will be in the future. Hopefully this is this. Okay. So I start with a disclaimer. I will talk about numerical modeling, nonlinear deformation analysis. So the behaviors we think we understand, we create equations that we put into the computer, and the computer will reproduce such behavior. We are not creating knowledge. We are simulating our perception of what is going on. Sometimes they look similar. So any resemblance with physical behavioral souls as we understand them today is intended, but sometimes we cannot make it. So it's always some sort of a compromise. And while nonlinear deformation analysis has a lot of uses, for instance, for informing monitoring systems and all sort of things, a bunch of things, today we will just focus on vulnerability assessment. So addressing the risk of a tailings dam to flow liquefaction. So these are the contents. All those phases are the team as we have it today. Of course, that is a moving target. Okay, what is a nonlinear deformation analysis? Well, it's the application of numerical methods to solve nonlinear differential equations. And our materials are nonlinear. Our problems have complex shapes, and we build in stages. So on the right side, you see a number of stress-strain behaviors that exist and are applied to some soils, rocks, or materials that we may use. On the left hand, you see an excavation, a civil excavation, with a lot of stages. You use a nonlinear deformation analysis to apply any of these behaviors that you see on the right to a problem that may be anything, a tunnel, an excavation, or a tailings dam. Where should we use nonlinear deformation analysis? Well, I compare with the limited equilibrium. It's an easy thing for me. In limited equilibrium and kinematics are only satisfied on the sliding surface, and we try a lot of them. Instead, in nonlinear deformation analysis, equilibrium and kinematics are satisfied in the full domain of the study. Limited equilibrium is rigid plastic, nonlinear deformation analysis, any of the many stress-strain relationships that we have seen in the previous slide. Limited equilibrium, fully drained or fully undrained, NDAs, also transient flow and consolidation. And limited equilibrium, no inertial forces, and a lot of inertial forces in the dynamic pore pressure. While I was speaking, the dam at the bottom right was shaking. Those were waves coming from a ground motion, from an earthquake, propagating with amplifications within the dam body. All this is easily achievable with nonlinear deformation analysis, and is way beyond what can be done with anything close to limited equilibrium analysis. So which are the ingredients of a good nonlinear deformation analysis? First, a good understanding of the problem in hand. So now we have this chart with this Castro 1969. It was already presented before in a much nicer format, but this is the original one. And this is a gentle blow on a pile of sand. Gentle blow, the sand liquefies, the full sand liquefies, not just where the blow is hit, and whatever is on top, that cylinder goes into the sand. So that's a good understanding of the problem. We need to do that. We need a good reason to use NDA, and we have so far a lot of presentations where when some simpler and other methods that stood this test of time, like limit equilibrium, when those can be used, let's use them. But you saw in previous presentation, you heard that if this is not working, throw to NDA, and we have been thrown a lot of these. So when it comes to NDA, nonlinear deformation analysis, it's because it's kind of the ICU of a dam. Everything else is already tried and failed. Then we need good input data, day one, good constitutive models. We're not going to fix this with more Coulomb or anything any close to that. A robust software, we are lucky that we have about 10 to 12 different software packages that now compete, providing solutions for this. A good model design, lots of quality assurance and quality control checks for the numerical aspects, not just for the geotechnical aspects. And a good interpretation of the results. Meanwhile, the poor box keeps getting some blows, and it keeps liquefying. So let's move into modeling the behavior of sands in monotonic shear. I'm not describing the real behavior of sands, may look similar. I am just saying how we model it, okay? This is the simulation. You see two gray lines and a blue line. The blue line is the isotropic consolidation line. It's not unique. You may be within the range because it depends on the formation ball ratio, the ball ratio at which you start this process. And you have your critical state line. They are not straight. They are not parallel. And you start at some point with some void ratio and no stress because you are in the isotropic consolidation line when you put the all-around pressure and no shear stress. And then you do a drained shear. And what you see is that in the left hand, the blue circle goes into the red, goes into the critical state line. This is a simulation, and you see a reduction in volume. The reduction in volume that you see, right hand, bottom figure, is proportional to the green area that is on top. This is stress dilatancy theory, and it's just like that. So when you want a different volume change, you can act on any of the things that modify that green shape on the top. Stiffness parameters, friction angle, a lot of things. Which things? The things that modify the shape of that thing. If the initial stiffness is higher, the surface, the green surface is smaller, the volumetric strength will be smaller. This is for drain shearing. When we go undrained, because the total volume cannot change, and we are talking about elastoplastic models, the elastic volumetric strain and the plastic volumetric strain must add up to 0. One plus the second one, total 0. This doesn't mean that there is no elastic and plastic volumetric strengths. There are equal and opposite signs. So what does it mean? That if you go and drain, the same green shape that you see right on the top will be responsible for the loss of confining pressure, or the loss of mean pressure. So the position of the red circle, right figure, at the bottom, is directly and uniquely defined by the area of the green stuff that is on top. This is how we model the thing with any of the constitutive models that are around. If a constitutive model is able to capture this behavior, it's because it has a good and solid stress dilatancy equation. It doesn't need anymore. Okay, choice of the constitutive model. There are several. There are many. The most popular today, I would say the most popular is NORSAND. It's very, very, very robust and very reliable, and there's a few buts. And also CASM, clay and sand model, was the one used by the Barcelona group, Arroyo and Jens for the Feijoa thing. It's very, very nice model, and some buts. All of them have limitations. HSS, the hardening soil with small strength plasticity available in Plaxis and now in FLAC, MIDAS, RS2, is also perfectly fit for this kind of undrained analysis. And I will click now, and you will see at the right hand what seems to be a picture is actually one of these moving things, and you will see undrained, the simulation of undrained triaxial shearing using NORSAND. I would like to, for you guys to see all the things in bottom right is going steady towards a critical state. Is this the proof that this is what soils do? No, again, disclaimer number one. We are simulating what we perceive is the real behavior of soils. If that is not the case, we're simulating something which is wrong. But this is close enough to our current understanding of the behavior of soils. So on the left, it is a movie of triaxial compression of something that liquefied. The thing fell down, like it fell down. So if you try to reproduce that, you may want to do what is called, and we always use this undrained plastic analysis when you impose zero volumes change to the full finite element mesh or whatever method you may be using. If you do that, you get this very nice localized formation, which is totally wrong. If you look at the right, there is no such thing as a localized shear deformation. What is happening in liquefaction? What is happening in liquefaction is that whatever is the softer portion of your real experimental sample will create a peak in pore pressure. This peak in pore pressure will propagate throughout the sample. It will not stay where it started. It will propagate at 1600 meters per second, which is the velocity of propagation of the sound in water. So the full sample will see an increase in pore water, and that will create the progressive failure. And you can model that with fully coupled flow liquefaction, which was advocated by Andy an hour ago. So let's move to, so these are the ingredients. Now we will make our meal. We will work about the vulnerability analysis of flow liquefaction. So let's state the problem using this kind of, using the model and pretending that the model replicates reality. So we have a dam, and we have this number 1 indicating a point that is not yet, it doesn't yet have any tailings, but now a raise, and this point now has some stress because it's located far away from the slope, but at some given depth. As we raise the dam, the point gets more and more load, and because it's so far away from the slope, it follows a K-knot compression. Now let's look at this second point, which started, if you go to the initial in the air as the first one, the first rise is also like point number 1 is far away from the slope, so it is again in K-knot conditions. But as you raise, the slope ends up to being above our point number 2. That creates more shear stress and less confining pressure. So the stress path of point number 2 is what is shown in the left-hand figure. And it's a drained stress path beyond that green instability line. That puts you in a dangerous condition. Now look what is happening in the circle, this stress rotation. You see that where the circle is, you see the lines rotating. This means that what is happening far from the slope is that stresses are increasing but stay vertical, close to the slope, they rotate. And they create this condition for instability. So instead of using the ICOLD chart, I'm using this one just because of the shape, the ratio. It's easy to use this for this presentation. So the current design practice is, do we have contractive materials? No or yes? Well, we're talking about conventional tailing, so we go to yes. We try with the factor of safety 1.5 or this much more elaborated and sound method that we now have in 194. And then we go to the concept that if it can liquefy, assume it will, we target 1.1. If you're lucky, no further analysis required, I have no job. But if it comes to my desk, efficacy didn't work. So now we need to assess the potential for strain softening and conduct triggering analysis for static liquefaction that have to be rigorous. And then this is when nonlinear deformation analysis comes to play in this game. But the idea of applying a lot of triggers looks appealing, it's time-consuming, and it's very difficult to interpret the results. So you get a number of results, and what? So what? What we are trying to do now is to group the many different things that may happen to a dam and bring it to failure into essentially three. Something that will happen close to the crest or at the beach, something that will happen at the toe, and anything that may happen within the dam, including the increase in phreatic surface. Why this? Because we have found that when you do risk assessments of what may happen at the crest or at the beach of the dam, you put in the same, I would say in the same bag, overtopping, flooding, the pond coming to the slope, a lot of things that are intermixed, interwinded, so you can treat them all as one, essentially. That is, can be challenged, and we're happy to do more tests, but I would say that these three, we must start with. And look at the lady. Can we claim that she's in equilibrium? She is, she's there. Is that equilibrium stable? We call it stable. If we do like this, like this small hammer blow to this lady, will she stay in equilibrium? The way we simulate this in nonlinear deformation analysis is we build the dam in coupled flow consolidation analysis, but at slow rate, so it's essentially drained, and we end to a point, and of course the point is particular to each point in the dam, but now we have this red circle representing the full dam as a concept. And what we do now is what Professor Furi presented in the previous presentation. We do nasty things to the dam to see how vulnerable it is to going across the instability line. So what we do? We know that liquefaction happens when it goes across the stability line, so we pull upwards by adding a crest load, a load at the beach. Why upwards? Because it increases both the pressure and the shear stress. So it's upwards and tilting to the right a little bit. We also put toe deformations or displacements at the toe. Why are we doing this? Because then you are reducing at the toe or close to the toe of the dam, you are reducing the horizontal stress. And by doing this, you are reducing the mean pressure and increasing the shear stress ratio. And the third one, which is a classic, you increase the phreatic surface that will reduce the mean pressure without changing the shear stresses. So we do all these three things. And we get values, a load of 100 kPa or a toe displacement of 3 meters. And those values never come to play, actually much smaller, or increase in the phreatic surface of 25 meters. If I am optimistic today. And we can plot them like this. So we have in this three-dimensional thing, which has units of load, meters, and percent. It's a very complex chart. We can test this, and we can also run these exercises, increasing the vulnerable, the triggers in couples. So we keep one of them constant and we increase the other two. If we do this, we can create sort of a vulnerability surface, can we put it that way? The combination of any of these three that may bring the dam to failure. So the idea is that we have here a cross-section of that vulnerability surface. The dam is somewhere, and all the analysis have some uncertainty, and we need to deal with that. So far, what is common, what is always used, is to check these three and say 100 kPa, 3 meters, or whatever the three values, and come to a discussion with the stakeholders whether if that is plausible or not. What I'm doing now is trying to create this combined action, were also mentioned by Professor Fourie, this combined action, so we have a lot of options, of things that we can consider whether if we can bring the dam to failure or not. So the sequence, we simulate the construction at a realistic rate. There will be some generation and dissipation for pressure. Then we still, for now, have to compute the short-term factor of safety. We compute it, we know it will not go well. Why do we know that? Because if we get a good result, it's not our job. Why are we doing NDA if this goes well? We just confirm. And then we apply these destabilizing actions. I refuse to use them as triggers, because in this case, I will raise the phreatic surface of a dam even in the desert. We are applying these actions even if they are not plausible. It's a vulnerability check. Very, very similar to the buckling of a column. You check buckling of a column, whether if the column is very robust or not. You do it and you pass. And the same here, you apply a load. Oh, the dam is closed, that load is impossible. You apply the load. You want to know whether if a small load might bring that dam to failure, even if the chances of that load happening are extremely small. A few things that greatly improve the results. First, you can use the soil-water characteristic curve and saturated soil mechanics for a smooth transition from saturated to dry behavior. This does not mean that you are using to your advantage the unsaturated shear strength, because what you do is you put a soil-water characteristic curve that is kind of fake and will create a rainbow zone, which is very narrow, and it will split the fully saturated to the dry behaviors. Why is this important? When you're applying the trigger of raising the phreatic surface, more and more material are becoming below the phreatic surface. Used to be above, becoming below. If each time you raise, you need to change the material parameters or remesh to say this is now contractive, used to be drained, that is a mess. And we can use this, and this is very, very robust, very reliable, and it just works. I will prove later. Also, add fully coupled flow deformation for mesh independency. As I showed a few slides ago, if you try to simulate the problem of liquefaction using just zero volume change, you get localized failure, which you don't want. You want to get your results that are reasonably independent of the numerical particularities, the mesh, everything else. So if you look at the left two figures, top and bottom, two very different meshes and the same result. And without any regularization technique. It just works. That is why we can use these Plaxis flaggers to modeling, and we're not working a lot with the regularization techniques of strain softening, because this particular strain softening is related to the propagation, the generation and propagation of pore pressure, which propagates around the mesh. You don't need extra features to do a reliable NDI, non-linear deformation analysis of a strain softening material, if the strain softening is an external consequence of the pore pressure buildup. But if you do all this, you have all these features, and you stick with the zero volume change throughout, then your result, the thickness of your sliding surface will depend on your mesh. You don't want that to happen because right hand up and down will give you different values. You don't want that to happen. Okay, so this is a close-up showing that in the left hand, the size of what is the sliding smear zone is independent of the element size, while on the right, it's all just happens to be one element thick. Oh, this is a nice example. Your highlighted is the load applied. To the left is the maximum load. Bottom right, you see the instability line, and a few points above and a lot of points below. Up left, excess pore pressure. Up right, shear strain. But now focus a little bit on bottom left, where at the toe, where the phreatic surface hits the ground, there is a few red points that are coming across the instability line. As we increase the load, note that the load went up to 196 and back to 22. Very nice slide, so I will play that again. Now I will ask you to focus on the excess pore pressure, top left. So you see it's a uniform mesh. The soil water characteristic curve is working, and it is creating excess pore pressure that are slowly going towards the slope. Do you see the excess pore pressure a little bit above the phreatic surface? That is a capillary zone. How do you define the capillary zone? Because you have the soil water characteristic curve. And now you have all this excess pore pressure and your dams goes down. Okay, sanity checks. You must check that your stress field before you started your analysis is realistic. In this case, we calibrated for K naught 0.6, but any value, whatever the most plausible K naught value that you want to use can be employed. And this is one thing. The other one, look at this. You are doing all this unsaturated soil mechanics, fully coupled flow deformation. It's a lot of things that you're putting together. So just check that when you apply a load at the surface, points that are far from the slope and below the phreatic surface, because you're applying this load fast, those points don't have time to consolidate. They don't have time to change their effective stresses. So you apply the load and look at the points that are there. I will have to go to the next one and back for you to know what I'm talking about. Those three red points in the down extreme right are stationary. Not here, but here. The red points are stationary. They are not moving because no changes are occurring in mean effective stress or shear stress. Why? Because whatever changes we are introducing there, far from the slope, are taken by the water. Classical undrained response. But if we take the same three dots that we see in the left-hand figure with the circle around, and we move them out above the phreatic surface, now they are no longer in the saturated zone, they are unsaturated. And because they are unsaturated, the load applied at the crest, at the beach, will create changes in effective stresses. And that is what you see in the extreme lower right figure, where all these points follow the K naught compression line as expected. Those are elements of soil that are subjected to vertical increase in stress, and they can drain because they are in the unsaturated zone. More interesting for what we're discussing is what we see in stress points located along we now know the failure surface. In numerical modeling, we don't predict where the failure surface is. We run, we see where there is, and we put the points there. And as you see, all those points started follow a line that I showed very, very early in my presentation. When you're close to the slope, you're not along a K naught line. It's a steeper one. If you put the starting point of all those lines, all of them very nicely plot on a straight line, and all of them go across the instability line and down to critical state conditions. You may notice that the end point of those red curves is not the dashed black line. That is because the dashed black line is conventionally defined for triaxial compression. And this is not triaxial compression, this is plane strain deformation. So it should not go to the critical state line defined at triaxial compression. Oh, this is nice. So I will play it twice. As we increase the load, we see the flow. This is very, very small blue arrows that are trying to move up. What is what they're trying to do? To increase the water table. When we apply the load, there is flow trying to move the water table up because of the coupled flow deformation. We put a load, and this extra pore pressure is trying to move the fractal surface up. That's what you see on the surface. And then essentially nothing happens in the body until a few points go across the instability line, and all of a sudden there is a lot of flow. What does it mean? That the extra pore pressure is propagating and it's affecting points nearby and creates the whole liquefaction. So back and forward. Things only happen at the very top, where the phreatic surface is attempting to move. And you see some shades now that will become nasty very soon. And it goes away. This is conventional coupled flow deformation analysis. Nothing different to what is off the shelf in the numerical modeling software that we have available. There's nothing, this is off the shelf, but it's using all the tools that we have in that toolbox. Okay, so now, on seismic liquefaction, we need to switch the constitutive model because none of the models that I described, CASM, NORSAND, HSS, none of these are any capable of predicting the behavior of salts in cyclic loading. So we start with something like HSS or any constitutive model that we may like to create the initial stress field, and then we switch to some other constitutive model capable of reproducing the cyclic behavior, for instance, PM for sand, PM for silt, P2P, sunny sand, but keeping the effective stress fields and the pore pressure fields that we got from the previous stage that was done monotonically in a static loading. And then we apply the ground motion. In NDA, everything else remains the same. There are numerical things you would need to take into account. How do you apply the motion, the absorbing boundaries? There are a lot of tricks that you have, things that you have to put in. But it's nothing extra from the point of view of theory other than adding the dynamics to what used to be a static analysis. And then, after this, you have shaken the thing, but for the post-seismic, and while it slows down and comes to repose again, this cannot be properly captured by PM for sand. It's not able to get that. So you need to switch back to the model that you use for the static loading with this extra pore pressure and see whether if the thing, now the earthquake is gone, is the thing coming down and stop? Or this extra pore pressure created by the earthquake will keep it going down the river? This is something you cannot address with using a PM4 sand only. Okay, so this is an example of calibration of PM4 sand. There's no information there. It's only that this is more or less the best you can do. The gray is the lab. The red is the simulation. You may see in bottom left, you see nothing. Top left, you see that they are not very similar, but this is the best we could do. Top right, this is the only one we would show if we were selling the thing. And bottom right is also looks very, very well. And now the new source of our Sanity, which is huge, is the seismic record. The idea that we are here and we found a seismic record close to here 25 years ago, and we use that one, is flawed. The uncertainty of the behavior of the dam for a given seismicity is huge. So for instance, we have this ground motion with an Arias intensity of 9.1 meters per second. It's a lot of energy. And this one is even worse, Arias intensity of 12.4 meters per second. For the same dam, the first one creates a displacement of 8 meters. The second one creates a displacement of 1 meter. So if you ask me, which of the two has more energy? The one below. Which of the two is creating more damage to the dam? The one above. Why? Look at the shape of the ground motion, the time history. So this kind of sinusoidal thing has a fundamental frequency which is closer to that of the dam. So it's heating and heating and heating again before the dam can come back to stable. The other one is more like this, you know? It's not doing much to the dam. So these are the shapes of the two outcomes. Left, less energy, but bad choice of frequency. Right, more energy, but harmless. And what we have found is the best prior for selecting ground motions, but with a lot of uncertainty, is to say, okay, let's check what are the fundamental frequencies of our dam, and now let's pick ground motions that will have the intensity measures, the seismicity indicators that will be relevant to the site, and from the hundreds of those that we may have, pick a few, say 20, not 3, say 20, that will have a frequency content that may be more damaging to the dam. We did that a number of times already. And this is, for instance, for a given problem, 20 plus 25 ground motions. And what you see left, bottom left, is the very, very sharp correlation, very, very nice correlation between the crest maximum displacement and the spectral power between 0 and 2 hertz. Easy. After you run, that 2 hertz was the threshold for this particular dam. Not that easy to do in advance. So that's why we need to run a lot of ground motions. So input, many seismic records. Output, the crest displacement is a statistical variable. We are not saying that the crest displacement here is 0.3 meters or 1.3 meters. We produce a probability density function. Given the seismicity of the site, we still don't know which will be the frequency content of the ground motion that will hit our dam. So we don't know what the crest displacement will be. It will be between this and this. And we cannot be more certain than that. Sometimes our clients or others say, provide us a value. I mean, don't create more problems. But this is what it is. You know, the uncertainty of ground motions is so large that is claiming something we don't know that we will have a certain value. What we can say here is that the probability of the displacement to be above, say, 1 meter is 5% or 1% or something. And that is multiplied by the probability of the ground motion coming, which is 1 in 2,500 years or whatever. So this is just a static slide showing for 3, 6, 12 shown there, for the same dam and 12 ground motion with the same PGA, totally different shapes, some of them including liquefied zones, some of them don't. And this is just related to the frequency, content, duration, blah, blah, a lot of things got related to the ground motion, and all of them for the same material parameters and the same geometry. Oh, this is a movie, so will give me a breath. Nothing very important here. Bottom, there is the shaking and the creation of excess pore pressure. Middle is the deformed shape. The upper one is just static. So you have enough pore pressure created in some layers, and now your dam is falling away. This result didn't mean that the dam failed. This is a scaled up deformation. This is one of the runs and created deformation maybe 8 meters or 6 meters or something. And after the ground motion stops, the dam stops, but 8 meters deformation is considered failure by me already. So now I'm moving forward, and this is a teaser only. I toned down this a little bit. How can we do one step towards leaving factor of safety behind and moving into probabilistic or semi-probabilistic design methods? Well, with all the information that we currently have, there is something we can do. So, you know that the industry is slowly moving away from factor of safety and into performance-based risk-informed design. Slowly, it's happening. It is in JSTM, it is in ICOLD. Well, what is performance-based risk-informed design? Is the combination of a set of features. Please read this paper by Professor Morgenstern. So intelligence dam design and operation at large and in a nutshell is taking into account failure modes and quantitative risk assessment. So I have now a team of people properly doing quantitative risk assessment and addressing the probability of nasty things happening to my dam. Bear in mind that we have this group already. And applying the observational method, which works for a lot of things, including for the precursors of flow liquefaction, but not for flow liquefaction itself, as has been perfectly explained before me. The brittleness means that once the thing starts, it will happen within seconds, so there's no early warning. So for flow liquefaction, the observational method is not applicable in cases where the failure mechanism is brittle. Vulnerability must be addressed at design level. That's what I think. Maybe I'm selling this now. Maybe there's a commercial component to it. But I do believe that the only sound way of addressing whether if your design is vulnerable or not is at design level. If you wait to build it and check that it is vulnerable, that is kind of too late. And NDA can inform an estimate of probability of failure. How? So we need to define what is our threshold, our acceptance of the reliability we are targeting to. Define a target. Annualized probability of failure 10 to -4, -5, no problem. Pick a number and leave it. We are not going to revisit the value after the result. This is cheating. We are not going to do that. So first, we pick a probability of failure that will be our target. Then, we need to find a procedure for selecting the material parameters that we will all agree as a starting point. We don't need to invent the wheel here. We do have Eurocode 7. In Eurocode 7, it's now mandatory that it's a mandatory procedure for selecting material parameters for all geotechnical engineering problems. For instance, if you are dealing with a pile, because the length of the shaft of the pile is much bigger than the scale of fluctuation, that is to say, the noise in the ground property that is controlling the strength of the shaft, you are not invited, you must use the average value. So the average on-drain shear strength applies to the shaft capacity of a pile. But in the tip of the pile, the volume of ground that is required to fail the tip of the pile is just about the size of the width of the pile, maybe a little bit more, but not more than that. And if the size of the ground, the volume of the ground that is required to get some expected behavior, for instance, in the tip of the pile, if this is on the same order or smaller than the scale of fluctuation of the relevant property there, for instance, friction angle at the tip of this pile in sand, then you must use a tail value with a probability of exceedance. In the most extreme cases, it's 5%. In most cases, there is a formula, and you end up with a tail of 10%. It's not by heart, it's not a consensus, 25, 23, 15, no. We have a formula, and we end up using the same thing. We can use all these, and once we agree this, we will discuss if factor of safety is 1.1 or 1.115, or we can decide some other things. But if we can agree on a method for determining the design material parameters, that would be very nice for our industry as a step forward. And because this has already been done for foundations, tunnels, retaining structures, civil slopes, highways, embankments, we may say, sound enough. How do we apply this to our problem? If we follow this idea, then for a particular failure surface, you will have a portion that will be largely horizontal. And because we are depositing tailings in horizontal layers, we might be unlucky. We might have had some slimes at the early beginning of our deposition. So for the horizontal surface, unless we can prove it otherwise, we should use a tail. In this case, I used this red line at 10% tail and ended up with 0.05, this very nasty undrainage stress ratio. But for whatever is at the backscarp, all that is going across all the layering. So the scale of fluctuation of our tailings as a geotechnical body is the layering. It's like this, more or less. And the shape of this is 50 meters. So we use average. So we go and end up with a much nicer residual undrainage stress ratio of 0.11. This is a proposal. This is the Eurocode way of doing this, but this is today a proposal. It's not true that this is an accepted procedure. And in this particular section, I am moving to the boundaries of what is accepted today. Third, call them in. We have all this group of people, and we ask them to compute the probability density functions of the actions defined in the demand, which is the probability of your crest load being 10 kPa, 20, 50, 100, 1,000. And they will give a set of values. And I put these probability density functions as very colorful, nice. In the screen, those figures are probably more colorful than they should be. And now we have them, and we come back to the numerical models, and we can use our standard procedure for estimating this vulnerability surface. Instead of just picking one undrainage stress ratio or one state parameter, we pick within a range. So our own shape is not fixed, deterministic, we know this. No, it also has this shadow, is glowing. We don't know exactly where it is. But once we have this, now it's easy. Because it's just doing Monte Carlo. We pick any one value from one action, from the PDF, from the probability density function of that action. We pick one value from the other, one value from the third one. We end up in 1 point. Is it below this 10th? We are safe. Is it above? Fails. We do it 100 million times. We can. And we end up computing the probability factor of failure of the dam by standard Monte Carlo analysis. How can you do this 1 million times? Because you only run these 6 numerical models, and you create this interpolation surface. And the other 3 colorful things was this group of people that we only met for a couple of mornings to get those numbers. And then this is very simple math. It's just Monte Carlo running from analytical equations. It can be done. This is beta testing. We didn't get it through a client and fully approved yet. I don't think so we'll have in 2024 or 2025. But this is our way of thinking in moving forward. Okay. So this is made up figures, and it's a movie. Now imagine on the left-hand side, you have a dam without a buttress, and you end up getting values for these 3 triggers. And if you do the math, we didn't do. If you do the math, you end up with a probability of failure of 10 to minus 2. Not acceptable because you have already decided 10 to minus 4 as a threshold. And you buttress the thing, and you see that the probability of failure is now 10 to minus 5, so you're okay. Maybe you see, okay, well, we can reduce that buttress. Yes, out of this, if the probability of failure is way below your target, you have some support for revisiting the size of your buttress. I'm closing. Takeaways. First, a lot of papers from our teamwork trying to prove that this, or what we are saying, is sound, and some of them are a little bit contradicting, I must admit, so please just read the recent ones. And our takeaways. First, modeling the undrained shearing of loose tailings is all about stress, strain, volume change in critical state soil mechanics. In undrained mode, there is no volume change, so it's stress, strain. Stress dilatancy theory, if you have it all. Then, upstream braces create a drain stress path towards unstable equilibrium that can trigger undrained failure. It's like the lady standing on her elbows. Third, vulnerability analysis deal, imperfectly, but as Professor Furi pointed it out, deals or attempts to deal with both the known and unknown unknowns. We try to do this. Of course we fail, but we try. It's a good thing to try. Instead of saying, in this particular dam there is no water, don't do that analysis, we run this set for the three of them, and we leave the risk assessment team to say the probability of the water table being this high is 10 to minus 8 or whatever. So we leave it to them. This is a way of splitting the uncertainty into the very sources of uncertainty and not combining them all into just one number, for instance, 1.5. In seismic analysis, it's more or less the same thing, the same tools, other constitutive models, of course, but please add the uncertainty of the ground motions. Use as many records as you have available, and bear in mind that they should have very different frequency contents, because the frequency content is largely overlooked and plays a major role in the outcome. And we have some ideas, preliminary ideas in test mode towards computing a probability of failures of tailings dams against flow liquefaction, or at least to have an estimate to inform the stakeholders about this. With this, I close. Small version of the pictures of the team. Without them, there will be no presentation, of course. Thank you.